When we're thinking about the scientific method, what would you summarize the scientific method in your own words? You're to sum it up. How would you sum up the scientific method? Does somebody have a
finding the solution to a problem by using experiments?
Finding the solution to a problem? Yeah, that could be. Sure. Any others? What do you think about the scientific method? Any other opinions about it? Finding the solution, how would you find the solution? Well, there are different types of solutions that people are after. And so when you say finding the solution, maybe somebody can be more specific in terms of what type of solution or... Scientists are good at doing what? Taking observations, right? What do they do with those observations? What's the whole point of what's the whole point of the scientific? What's the whole point of science in general? Yeah. To find scientific laws, that could be one of the solutions that people are after. They just want to figure out the law, like the ideal gas law. Why? Because the usual laws are just simple equations or simple concepts that you can apply to different things, right? And so that could be a solution. But what else? This is why, this is why it's helpful to sometimes put things in your own words. So what's the purpose of memorizing this list? Is it just so that you can repeat it? When somebody asks you the steps? So yeah, we might be after a law. That was like in this problem here. Do you see this equation here? This equation here is what we call empirical equation. This could be a law. This could be the law of the variation in density based on the composition of a mixture of, do you guys remember what this makes? Naphthalene and benzene mixture. The two organic liquids that mix pretty well. They're hydrocarbons. And so, well, what's the use of having something like this? The use of having something like this is, with this equation, you can easily calculate the density at any percent composition. Or if you measure the density of a mixture, an unknown mixture, and it's a two-component mixture consisting of naphthalene and benzene, if you know that density, then you can figure out the percent composition. And so, yeah, the scientific method we can use to derive laws. Laws can be quite useful like this, right? But ultimately, what do we want? When you look at the scientific method, the ultimate goal of the scientific method is to gain what? Knowledge, but what kind of knowledge? This is where you have to come up, you have to know the jargon, so to speak.
Precedent?
Not precedents. Did you catch the video from day one?
No.
You got I listed the steps, but you can see it. It's the theory, right? Ultimately, we're into looking for the theory because the theory is what? What is the theory? this is kind of, you know, at the beginning I'm going to do this. I'm going to review it for you to make sure you catch it. But pretty soon I don't have time to review anything. I'm just going to keep going whether you catch it or not, you know, and it's going to be your responsibility to go and look it up. But what is a theory? Ultimately we want a general description. We don't call it a general description. We call it a fundamental description. That's it. I misheard you. Fundamental description, right? We want what is a fundamental description of what's going on? Is a fundamental description an equation like this? Do you understand anything about the mixture and how it behaves because of this equation? Well, we see, this is empirical. This is an empirical equation. This is based on, empirical equations are based on observations. Observations are what we call scientific facts. Scientific facts, as long as they were taken and they can be reproduced, right, are facts. You know, are theories always scientific facts? No, but whatever theory you come up with, it has to explain the scientific facts. If the theory conflicts with scientific facts, then the theory must be modified or, you know, abandoned. And so, what this doesn't really give us a fundamental description of what's happening in a mixture of naphthalene and benzene, does it? No, even though, yeah, it doesn't. And so where do we head from here? You know, why does it show this bizarre second order type behavior? You know, why isn't it just a nice linear thing like methanol and ethanol? You know, people start wondering that. You know, why is this so weird? The behavior of a naphthalene benzene mixture. And so what do they do next? Somebody thinks about it and comes up with a explanation, which we call a hypothesis, right? And so the next step here is, yeah, we can use this law, but, you know, sometimes we want to know, or we want to have a better understanding of things, so we need to hypothesize what exactly is happening in this, right? What exactly is happening here? And then hopefully we can either come up with some, you know, theory, or we can use an existing theory to help understand this, correct? And so this is the scientific method. We're trying to gain a better understanding. And where should we start in trying to get a better fundamental understanding about this mixture? Where do you want to start in trying to understand why does it have this mathematical relationship that describes the density of this mixture, you know? It's dependent on the square of the percent naphthalene. You know, this seems unusual. And so where should we start in trying to understand the, or where would you start in trying to understand this fundamentally? So what the heck is a fundamental explanation? What the heck, what is a fundamental explanation to you? So we start thinking about, you know, what it's made out of. Right? What is naphthalene? What is benzene? And so the first thing you'd want to know is what are the composition and, not just composition, but composition and, you know, in other words, what is naphthalene made out of? What is benzene made out of? We want to know the composition. And not only do we want, well, I'll tell you what the composition is. It's made out of carbon and hydrogen atoms. It's called, those both are called hydrocarbons. And they don't mix with water. Hydrocarbons and water don't mix. So we know what the composition is made out of carbon and hydrogen. We want to know what ratios, you know, carbon to hydrogen we have. And we want to know what?
Chemical formula.
Well, the chemical formula is the composition, so I didn't say chemical formula, but I could have, you know, just said we want to know the chemical formula. What is composition? Chemical formula is what we call the mole or atom composition. Another type of composition is the percent composition by mass, and so we use those, you know, in this case, this is percent composition by mass. Sometimes we'll do percent composition by mole. Chemical formulas are always mole percents or atom percent, or just ratios, atom ratios. So they aren't really percentages; they're ratios. So the composition and what else? Just because we have the formula, we also need what? So, you know, let's say your car broke down. You could just leave the hood down and just leave it as like a kind of a black box or something. Or you could start kind of digging around. If you dig around in there, what are you looking for? Well, maybe something out of place or out of ordinary or something. Not that you would do that, but, you know, or if something breaks, what do you do? You could throw it away, get a new one maybe, but let's say you try to fix it. If you try to fix it, what do you start doing? You would start looking at how things were put together, wouldn't you? In other words, we have something called structure, which tells us, you know, how it's put together. And so basically, scientists, chemists in general will look at composition, structure, and based on the composition and structure, they'll try to figure out something about the properties of what's going on. And so this is what scientists do a lot, you know, in gaining a fundamental understanding. They want to know the composition, structure, and the properties, you know, and that'll give a more fundamental understanding of what's going on, you know. And so we look at those types of things in this type of mixture and see, why do we have this weird equation defining the density? So, you know, a long time ago, around, I don't know the dates. You don't have to know the dates, but a long time ago, you know, there's an observation. The observation was that the mass before and after reaction didn't change, right? Observation came out. And so somebody wanted to come up with a fundamental description of what was going on because mass was conserved. I mean, they had this law called the conservation of mass and conservation of matter. And so, you know, to gain a more fundamental understanding of that, they came up with some kind of structural, you know, interpretation of what was going on. And based on the structural interpretation of what was going on, what was hypothesized for the conservation of mass, law of conservation of mass? You know, just like this law, you know, somebody gave a lot of thought into it. And so this, I know some people know because they wrote it down, but what was hypothesized about that? about why matter was conserved in chemical reactions. I know a lot of people didn't catch it, and so this is why I'm going through this now, because of looking at the results of the quiz yesterday. But at least, why, what was the fundamental explanation of what was going on with the conservation of matter? Does somebody know the hypothesis? Those of you who know, just keep quiet for a minute, but let's get. What's going on with that?
Atoms are neither created.
It's not, that's the theory. What was the hypothesis? The theory, that's part of the theory. Atoms are neither created nor destroyed. That's assuming that atoms are already accepted. But what was the hypothesis behind the conservation of matter? It does have to do with energy, but we aren't going to talk about that until later. And so this, actually anybody tell me. What it is. For example, let me tell you, the conservation of matter led to what? So first, see if it's in your notes. Oh, I just wanted you to do a quick note check and see when we first started talking about the scientific method. What do you have written in your notes as an example of the scientific method? Okay, gravity, gravitational force. Okay, skip that example and go to the next example. I gave 2 examples of the scientific method. Burning a candle, right. Burning a candle is one. Capturing the gases. And then that led to what?
There was in the same amount of mass within the closed environment before and after.
Okay, which led to what? Which law?
Conservation.
Which led to what hypothesis? Do you have it in there?
No.
No, you don't have it in there. Did somebody write it down, or they didn't write it down? Nobody wrote it down? The law of the conservation of mass led to what hypothesis? Nobody had it written down?
Mass consists of atoms.
Yeah, matter, not mass. Matter consists of atoms, which led to what theory? Which led to Dalton's atomic theory. Exactly. And so think about this. What evidence did Dalton have? In Dalton's atomic theory, one of the things is atoms are neither created or destroyed. But the first thing with Dalton's atomic theory is that matter consists of atoms. And so in Dalton's time, what proof did he have? What proof did Dalton have to convince somebody that atoms do exist? What experimental facts? You know, experimental facts are proof, right? What experimental facts did Dalton have that atoms exist? Did Dalton, I know some people, I don't know if it was this class, maybe it was this class, some people were saying, like, you know, scanning tunneling microscopes, scanning tunneling or, you know, those types of, not like electron microscopes, but these tunneling microscopes. They can manipulate single atoms. They can see single atoms on the surface. You know, there's plenty of evidence that you could cite. You know, nowadays, nobody disputes atoms exist because people have manipulated single atoms with these tiny, tiny probes and moved them around, right? And you can't break those down further. They're spherical in shape. And so single atoms, nobody disputes that because nowadays the evidence is overwhelming. You know, X-rays, have you ever heard of something like X-ray crystallography? You can't see atoms with visible light because of the wavelength. You know, but because of the wavelength of X-rays, you can see atoms with X-rays. They actually bounce off the electron cloud. And we don't have a lens that refocuses X-rays, so you use a computer to refocus the image of the atoms from the X-rays, and you get what's called an X-ray crystal structure, where you can see the individual atoms in molecules or other solids. And so there's plenty of modern day evidence that atoms exist. But some things, you know, some things are a little shaky. For example, like the Rutherford experiment. Does the Rutherford experiment prove that atoms exist? Well, yes and no, because you could say it proved what the Rutherford experiment did is that it was evidence for the nuclear atom model versus the what was the other model that was competing at that time? Nuclear atom model versus the, and remember this? One thing that will help you for sure is just review your Chem 4 notes. You don't have to reread the entire book, but if you review your Chem 4 notes, you know, because a lot of the first 4 chapters, in fact, these first 4 chapters are usually skipped at UCLA. You skip them and go into the meaty stuff. You know, there's no review. And so the other model was the plum pudding model. Remember that? Or I forgot what they called it in Chem 4. I think they called it the plum pudding model, right? That was it. Well, there are other things like, you know, do electrons prove the existence of atoms? Not necessarily, because electrons could be a component of something else, some ether. But going back to Dalton's time, the only proof that he had was that. I have a question. Wasn't it Thomson who made the plum pudding model? I'm sorry? Wasn't it Thomson who made the plum pudding model? No, Thomson did something else. J.J. Thomson discovered the electron. He didn't discover the electron. He discovered that the electron was a fundamental part of all matter. And he used something called the cathode ray tube, and in which the electrons get ejected from what we call the electrodes in a cathode ray tube. And you make the cathode rays a beam of electrons. And so what he did was he changed the material for the electrode. And no matter what material he used for the electrode, as long as it conducted electricity, he got the same beam of cathode rays. And therefore he concluded that electrons are a fundamental part of all matter because no matter what he changed it, aluminum, iron, whatever he used for that platinum, he still got the same beam of cathode rays. And then he concluded, well, whatever makes those cathode rays is a part of all matter. You know, he didn't test all matter, but, you know, he inferred it from that. And so J.J. Thomson discovered that electrons are a fundamental part of all matter. And then with the cathode rays, additional experiments with cathode rays in a magnetic field, people were able to get something called the mass-to-charge ratio for the electron. And the mass-to-charge ratio from the cathode ray plus Millikan's experiment. Do you know what Millikan did? What Millikan determined in the oil drop experiment? I don't know. Did you guys cover the oil drop? For sure the cathode ray you covered, because remember that. You should have covered the Millikan oil drop experiment. The Millikan oil drop experiment, he got the fundamental charge of an electron. And in fact, if you go to Griffith, I was there, I don't know if it's still there, but when I was a student at UCLA, I went up there. to Griffith to look at the Millikan oil drop experiment. There's a little telescope you can look at, and you see all these oil droplets coming down. It's pretty cool. But he got the charge on an electron. And so from the charge and the mass-to-charge ratio, you can get the mass of an electron, which is extremely small. And so how do you weigh a single electron? That's how you weigh a single electron. You can't put a single electron on a balance and weigh it. Impossible. But they were able to get the mass by using the cathode ray tube, magnets, and Millikan oil drop. You have to know those. At least you should know the big experiments. The big experiments were Rutherford. What did Rutherford do? Gold foil experiment. What did Rutherford's experiment determine? Nuclear atom model. Thomson. Cathode ray tube. What did the cathode ray tube determine? The electron is a fundamental part of all matter. Also, the charge, mass-to-charge ratio, it turns out the electrons were negatively charged. You can easily determine that based on putting positive and negative plates there and see where the electrons are directed to. The mass-to-charge ratio. Although Thomson didn't do the mass-to-charge ratio, that came later. And then Millikan, what did Millikan do? The oil drop experiment. And what was the main conclusion of the oil drop experiment? Mass, not the mass of an electron. That came after calculation. The charge on an electron. The charge on an electron. And then using dimensional analysis, you can calculate the mass of the electron. The original calculated mass for the electron was way off due to, the precision and accuracy of the measurements. It's been fine-tuned, and so now they know to a lot of sig figs. Those experiments you should know, but those weren't used in determining atoms. So imagine you're Dalton. You're Dalton, and somebody passes you a book. They say, I don't believe in atoms. And then what would Dalton say to them? I have evidence, right? What was Dalton's evidence that atoms exist? The experimental evidence of conservation of matter. But, somebody would say, hey, my theory explains the conservation of matter too. There's this ether, and this ether just moves around, and it weighs the same, and it just changes form. It's like, what do they call, like those aliens that can change form, go from one substance to another, right? This ether can do the same thing. That's my theory of what matter consists of, right? And so then, obviously, imagine you're Dalton. Do you think that's easy to argue that atoms exist based on the conservation of matter? Dalton certainly didn't have a STM, scanning tunneling microscope to say, look. He didn't have X-ray diffractometer to shoot a beam of X-rays at a single crystal and get an image of the atoms in a molecule, did he? Or solid? No. What did he do? He just had the conservation of matter. And the point of this is it's still relevant. You think that's ancient times. Nowadays we have so much sophisticated machinery and all this other stuff, right? But the same issue comes up. If you're to go on and let's say pursue something like a PhD or do your research or work at some company, you're going to be hit with this point. Do you think you're always going to be repeating somebody's calculation? Do you think when you start working in science, do you think there's always a solutions guide, or there's always an answer, or you can ask somebody for the right answer? Once you start working, there's nobody, you're going to ask for the right answer, because who's going to pay you to keep repeating somebody else's work, right? It just doesn't make sense. They're going to pay you to do something new, and when you do something new, right, you're going to be out there like Dalton saying, okay, this is my hypothesis, or this is, my conclusion based on what these experimental observations mean. And it's not so easy. I'll tell you, you know, if in getting a PhD, some people take a very long time. Some people take a very short time. I'll tell you, if everybody's experiment worked perfectly and everybody got beautiful data, right, then getting a PhD is very fast. But the problem is you get a lot of data with a lot of uncertainty, and you just don't know how to interpret it properly. And then it gets very slow. And there's a lot of uncertainty, so how do you deal with that in certain things? You know, obviously everybody wishes for nice data, and in fact, there's even examples where people, you know, fudge the data. They fudge the data because it doesn't agree with, you know, their hypothesis, and so they make it agree. You know, but that type of stuff is quickly caught. You know, for example, a paper that went out to Nature, you know, was recently learned that, you know, the people fudge the data. It was quickly caught, and then the paper was retracted from Nature, and then the people who wrote it resigned from their position, you know? There's a lot of pressure there. And it's not easy. It's like you're Dalton all over again, but now, rather than working with simpler stuff, you're working with a lot more complicated things. And so this is why you got to start thinking like this now, so that, you know, when you get on, you're already, you know, accustomed to what they call, you know, critically thinking about your results. A lot of people don't critically think about their results. They leave it to the critics. But what you should do is self-criticize your results to see, you know, before presenting it. Because you go to these conferences, you see people get blasted because they have so many holes in their presentation, you know, and they should have gone through some more This is the whole process of science. The whole process of science is this, as I mentioned before, if taking criticism is difficult for you, then, you know, science isn't the place to be, because that's all you're going to get. You're just going to get criticized, 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 because it's a self-policing kind of organization, and all the junk stuff hopefully is filtered out. Not all of it, because some of it doesn't get caught, right? But a lot of it is. And so the best thing is to start, you know, thinking about what types of questions would get asked, you know, for this. Well, the first thing is, before you get that, you just have to build the standard fundamental base. And so, you know, I was talking about medical school. Do you think, if I asked this same thing to somebody who's pre-med, you know, and the class was hyper-competitive, do you think a lot of people would have said, well, one piece of evidence is the conservation of matter, because they had read it a few times? You know, that's what led to atomic theory. You're competing against, you know, you got to think, if you want to go to medical school, and I know a number of you do, you really have to step up, you know, and be prepared for a little bit more work. Well, actually, a lot more work. You gotta be more on top of it. But if you're not, you know, if it's not the hyper-competitive, you just learn it as you go. All right, I'm not going to belabor it anymore at that point. But anyway, let's go back to atoms, and let's talk about atoms. So we want to understand how matter works. If you want to understand how matter works, you better know what? We want to know how matter works because chemists study matter. What is matter? Matter is the physical material of the universe. Everything. And so if we want to understand matter, we need to know how it works. Well, how do we figure out how matter works? How matter works is what we call the properties of matter. You know, the properties tell us how matter works, you know? And so what do we need to know, or what should we start digging into to get a better fundamental picture of how matter works? Well, in chemistry, we have a two-pronged approach, you know? In chemistry, we memorize a lot of how matter works. For example, water. Water is a liquid, you know, under normal conditions. Chlorine is a gas, right? Chlorine is a gas. What about bromine? Liquid, gas, or solid? Liquid, that's good. You guys have memorized that. Well, a lot of people hate memorization, and they go, well, I don't want to memorize anything. If you don't want to memorize anything, then somebody asks you, what is iodine? Solid, liquid, or gas? Tell me how you're going to figure it out. Well, they say, well, I'll just look it up, Google it or something, right? That's possible too. You don't have to know everything. But there's certain basic knowledge that everyone should know, and that basic knowledge is going to help you put things into context. And so, if you don't know what iodine is, no big deal. But you should try to memorize, as much as you can. That way, you know what's reasonable. And then you can put context into theory, because the other approach is to understand it theoretically. So for example, prove that iodine is a solid theoretically. How would you do that? Prove that iodine is a solid at room temperature, 1 atmosphere pressure, theoretically. It's too much work, too hard. Much easier just to memorize it and then use the theory in certain contexts. That would be a difficult calculation, especially by hand. And so, some of the stuff in terms of theory is very tough. But ultimately, we want a theory. And so how many theories are there? Well, there's atomic theory. And now Dalton's atomic theory says what? Well, atoms are neither created nor destroyed. What else does Dalton's atomic theory say? The smallest fundamental piece of matter is the atom. Right? Dalton's atomic theory said that atoms are all identical. Is that still correct? No. Dalton's theory had to be modified because all atoms of an element are not identical. Excuse me, I should have said of an element. Because we know what exists. Isotopes. Isotopes are atoms of the same element but with different mass numbers. In other words, different masses or different numbers of neutrons. Right? They all have the same number of protons. That's what identifies an atom. He said atoms are neither created nor destroyed. Is that 100% correct? No, because Dalton didn't know about nuclear reactions. In nuclear reactions, atoms can be created and destroyed, right? Certain sense. But that's okay, because nuclear chemistry and chemistry abide by different set of rules. Chemistry, do you know what's most important in chemistry? This is something I skipped in chapter 1. It's discussed in chapter 1, but I thought I'll talk about it now. What is the most important thing? What is the most important, let's say, what is the most important force of nature for chemists? Are chemists mostly concerned about gravitational forces? Yeah, chemists aren't concerned about gravitational. Are chemists most concerned about nuclear forces? Most chemists aren't. Only the nuclear chemists are concerned about nuclear forces, because the nuclear chemists work on nuclear reactions. But chemists just deal with ordinary chemical reactions, which the most important force in ordinary chemical reactions, and also physical properties, boiling point, melting point, etc., bonds, is what? It turns out it's electrical forces. And so are you familiar with electrical forces? For electrical forces, again, this is chapter 1. Electrical forces have a simple rule. Opposite charges attract, like charges repel. if we take a lot of observations, then we can come up with something called Coulomb's law. You know, the Coulomb's law gives us the force of attraction. This is an empirical equation that just describes, you know, how these bodies are attracted to each other. It also can be derived from theory, you know, as well. But Coulomb's law says that, I'm just going to simplify it. It's going to be that the force is proportional to the charge, which we call Q. This is the charge on body A times the charge on body B divided by the distance between the center of charges squared. So this is, you know, to understand chemistry at the basic level, this is it. You know, chemistry is all electrical interactions. And so what we want to do is just understand all the electrical interactions that are occurring in chemistry. So Dalton's law, you know, or not Dalton's law, what was it called? Dalton's atomic theory. That was the first meaningful atomic theory, and it's since been modified. And so today we just have the modern day atomic theory. Modern day atomic theory just says that matter is made up of atoms. But the thing is, modern day atomic, oh, so what? Now we can see the atoms, you know, using instruments. If you can see the atoms using instruments, it's like looking at a car or something and saying, okay, it's a nice looking car, but, you know, how does it move? You know, how does it behave? What are the properties of that car, right? In order to understand the properties of the car, what do we need to know? How's it made? And how's it made deals with two things in science. How's it made is dealt with via what? Structure and composition. And so, okay, now we got atomic theory, matter is made up of atoms. Do you guys all believe that? I believe it, right? Because there's tons of evidence. I have a lot of respect for Dalton. You know, I always think about Dalton. I always think about Dalton when you're up there trying to defend your whatever, you know, your position or your hypothesis or whatever you are. You know, you got to think back at Dalton. He came up with the defense of, you know, atomic theory using conservation of matter, which seems kind of shaky, doesn't it? Would you believe Dalton if he just said, "Oh, matter is conserved"? Oh, yeah, it's clear to me now. Atoms must be atoms, right? But Dalton also, you know, something that helped Dalton's atomic theory is that theory should also be able to do what? A theory must give a fundamental description of whatever experimental observations, facts we see, plus what? Theories must be able to do two things. What's the second thing? Be applied to other situations. But it's not just like a simple law, like that density law. Other situations aren't, oh, I got, you know, 35% naphthalene versus 40% naphthalene. You know, it's not a situation like that. There's a qualifier on the situation. What was the qualifier on the situation? It can't be just any situation. It has to be, Just flip back in your notes and see if it's in your notes. Theories must be able to
predict unforeseen observation.
I'm sorry?
Predicting unforeseen observation.
Yes, exactly. Theories, the second part is a theory must be able to predict new unforeseen observations that people, weren't expecting, let's say. What helped the argument in favor of atomic theory? What helped the argument in favor of atomic theory? What unforeseen new observation helped? This is, this is why, like, when I was talking about that guy with photographic memory, you should check out that video about memory. I thought, wow, if you have photographic memory, then you're pretty much guaranteed an A in any course, right? Because 90%, what I found is 90% of the tests are like regurgitation of material that was discussed in class. It's just, you don't have to think of anything new. All you have to do is retain or be able to regurgitate that knowledge that somebody else told you. And so it's not real thinking. And then maybe 10% is like applying it to something new and unforeseen, right? A lot of people will argue, I never gave anything like that, but my tests are a little bit different. I'm just telling what to expect or what I saw for most classes. And so if you could just regurgitate the knowledge, that was, or just whatever was said in class on the test, then you pretty much got an A. If you want the top grade in the class, then you're going to have to do a little beyond that, have some kind of, way to apply it beyond that. And so here, think about this. If you can't, regurgitate it, then you're putting yourself at a big disadvantage. So just try to get it in your memory. And memory fades, right? That was day one. Think about it. That was day one, which was Monday. Think about what your memory is going to be like in 1 month. That's going to be long gone, right? Long gone. So I want everybody to do well in this class because I don't like giving bad grades, but it happens. And if everybody gets an A, then I'd be happy to give everybody an A. But I'm not going to do it if it's not an A material. Anyway, let's go back. What new unforeseen result was helped? Helped Dalton's atomic theory considerably. That people thought, now it's starting to make more sense that matter consists of atoms. Okay, well, for regurgitation, this is why I thought it was so important for the notes. Because in order to regurgitate that, I first had to have it written down so I could remember to regurgitate it during the test, right? Maybe regurgitate is not the best word for this, or just recall the information for the test, right? But if my notes weren't complete, then I'm missing it and I'm hurting myself. Maybe I'm now at 88%, 85%, 80%. And if you get asked that question and you don't recall it, then you just lost some points. You don't want to lose points. And so the first thing is to write it down. Did anybody write it down? If you don't have it written down, then automatically, of course you're going to lose those points, right? Unless you have a photographic memory. Like I said, I don't like giving low grades, and so not that I would ask this question on a test, but if I did, everybody would have gotten it wrong. Probably would have asked it on multiple choice. So you might have guessed it right. Or, if you read the answer, it might be in your subconscious. Nobody wrote it down? Vice versa. If everybody gets a C, then I don't mind giving everybody a C and no A's, I don't like giving lower than a C. I hate it, but it happens every semester. What was the new one for? It was called the Law of Multiple Proportions. Law of Multiple. I actually wrote that down on the board. And so Law of Multiple Proportions, you can go back and read about that in your intro book or in this book, because Law of Multiple Proportions is talked about in chapter 2. And so And so we want to understand how atoms behave, and we're going to also be thinking in terms of electrical forces as well, because electrical forces are so important in chemistry. And so when we're looking at structure and properties, you know, in the back of our mind, we're always thinking about electrical as well. You know, because you guys know the protons are what charge? Positive. Electrons are negative, and neutrons are neutral. So there we go. That's a lot of the structure and properties there. And so what I'm going to do is, you know, you can review Dalton's atomic theory. It doesn't take very long. It's like 4 or 5 statements. But we're going to go to the structure of atoms now, because once we get over this hump, you know, of believing in atoms, then we want to know how atoms are structured, you know, how they operate. What is the composition of an atom? Somebody tell me the composition of an atom. Or what do atoms look like? Even though nobody's seen an atom with their eyes, you know, people have seen atoms with instruments. And so what do the atoms look like? They're spherical. Now, do atoms have a hard shell, like an egg shell or something like that? No. And so that's a little tricky. And so if I draw a circle like this, what does that represent? This represents the relative size of the atom. You know, the size of the atom actually that you find in books are averages, because the size of the atoms vary depending on what you bond it with. Some things can bond more tightly and squeeze in closer. Other things can't bond as tightly and don't squeeze in as close. And so what you do is you take a large number of data and get the average size of that atom according to the data. Now, the data sets vary in numbers. You know, if you had an average that was based on 100 versus an average that was based on 2 observations, you know, then the average that's based on 100, you'd feel a lot more confident in, wouldn't you? But those tables don't give us that kind of information, unfortunately. They don't tell us how many atoms that average was based on. They just give us the average, so we'll just use it. And so we represent this, the average diameter, by some kind of circle. And what else do we know about the structure of this atom? Well, from what experiment was it determined that most of the mass, and in fact nearly the entire mass of the atom and all its positive charge is in the nucleus? What experiment determined that? The Rutherford. The atom consists of mostly empty space. In which the electrons are found. I'm going to stop soon so we can go on break. Electrons are here. Mostly empty space with electrons. How were the electrons discovered again? Millikan? Did Millikan discover the electrons? True or false? Thomson. Yeah. And so the electrons are just, this is from Thomson. And what was the instrument he used? Cathode ray tube, CRT for short. So we know there's electrons there. And the electrons, you know, what can we say about the electrons? You know, we want to understand electrons. Okay, one, we can say in chapter 2, actually, there's a table. We'll take a look at that after the break. But what do you want to know about the electrons? Tell me what you want to know. You know, we're trying to figure out how things operate. And so what do you want to know about the electron in order to understand its properties? the structure and the composition, and whatever. Well, it's tricky because electron is an electron. It's a fundamental piece of matter, subatomic particle. What exactly is electron made out of? I don't know. It's just an electron, right? But we can know some of the properties of the electron in terms of charge. It has a negative charge. How was the charge discovered? The oil drop. That was, what was his name? Millikan. Oil drop. And we'll look up the charge. It was like 1.6. 10 to the minus 31, or 10 to the minus 19 coulombs, something like that. You don't have to have it memorized. But you do have to have this memorized. Rather than memory, we call it a -1 fundamental unit of charge. Okay. Let's stop here. I don't want to go too long. I'll have a break. So we're going to take a break and then we're going to continue this.